Okay, so we're jumping into our last chapter. Yay! Can't believe we're almost done. Which is exponential and logarithmic functions. Today we're mainly looking at exponential functions, meaning they have exponents that are variables. Logarithms, that button on your calculator that says log, that is used. Now you're all like, wait, there's a button on here that says log. That button is used to help you solve for exponents when you're trying to figure out what they are. So, yes, log, L-O-G. Huh? Log. Log. So for today, we're mainly looking at exponentials, though, okay? We're actually covering sections 7.1 and 7.2 today, exploring exponential models and then properties of exponential functions. So logs we'll really get more into tomorrow. All the exponents is today. All right, so first thing is an exponential function. Its general form, f of x. What does f of x mean? It's just like y. It's a function, yeah. It's an equation. So f of x, or y, equals a times, bless you, a times b to the x power. So my unknown is my variable this time, which usually that doesn't happen. Says a cannot equal 0. Why would you not want a to be 0? It's good, then everything would equal 0, because a times 0 times anything is 0. So that makes my equation not any fun. And then b has to be greater than 0. We want that to be a positive number. And b is not 1, because 1 to any exponent is just 1. So that's no fun either. Right? X is just any real number. It's not imaginary. Okay. So first, before we actually get much into it, it's like, what does the graph look like? So we're going to actually practice. We're going to graph by hand a little bit, which we can handle. So normally when I have you to graph by hand, we make this big XY table and all of this stuff. What numbers do you normally plug in? Do you remember? -2, -1, 0, 1, 2. Right, for x, and then we plug them in and see what we get for y. All right, so if I plug in a -2, let's do this without a calculator for a moment. I know some of you are so calculator dependent. Tori, the look on your face when I said that was like, oh, like really? Do we have to do this without the calculator? But yes. So if I do this to a -2 right here, what does a negative exponent do to my number? I need you to know this to lead us into tomorrow's lesson. What does a negative exponent do? It's going to push it down, right? So this is going to become 1 over 4 squared. 4 squared is 16. So 1 over 16. So what is half times 1 over 16? 1 over 32. When you multiply fractions, you multiply the top, multiply the bottom. All right, what if I plug in a -1? So 4 to the -1, the negative is going to push it down, so it's 1 over 4. And then half times 4th is 1 over 8. Okay, if I plug in a 0. What? Order of operations, say you do exponents before you multiply. Not how math works, though. All right, anything to the 0 power equals 1. Thank you, Quinn. 1. So that means that's not 4 to the first. That means it is literally just 1. So what is 1 times half? It wasn't a trick question. All right, if I plug in a 1, 4 to the first is 4, and half of 4 is 2. If I plug in a 2, 4 squared, and half of 16 is 8. Okay. We get away from the fractions. You guys do a little better. All right, so let's go actually plot some of these and kind of see what happens. Obviously, I got fractions, so it's not going to be exact, but -2, 1 over 32nd. What's that between? Okay, is it closer to 1 or closer to 0? It's closer to 0. That's all right. So it's going to be, I mean, as exact as I can be, right? It's going to be back 2, it's going to be up just slightly off the line, right? All right, and then -1, 1/8. So is it just slightly higher than that? I can't be real exact, right? But It's back 1, and it's slightly higher than that one. And then 0, half. I know where half is. I do you? And then we have 1, 2. And then 2, 8. Look at that thing. Now, the question is, if I went further negative, will it ever drop below that line? It's never going to drop below 0. So if you kind of draw this line in, oh, that was a terrible line. It keeps getting closer and closer and closer and closer and closer, but will it ever touch it? Your calculator may say it will because it can't hold all those digits, but will it truly ever touch it? It really won't. All right. What we just looked at, it's called an asymptote. Just so you guys know what that's called, an asymptote is where it gets really, really close to a line, but it never actually will touch it. Okay? Is that a positive or a negative asymptote? Positive. It's going up. From left to right, it is going up, so that was a positive asymptote. So, just so you guys are aware, that's what that is called.
Oh, so no matter how low the number, no matter how
right.
low the number you put in,
it's never going to drop. It's never going to be 0, and it's never going to go into the negatives. Yep, no matter what you do. All right, so let's kind of look at just some basic calculator function buttons, right? Let's make sure we're okay here. Can you evaluate 2 to the x power when x is negative 3.1? Grab your calculators. Yay, everybody's happy now. Grab your calculators. And what is 2 to the negative 3.1 power? Did you get an answer? What'd you get? A decimal. That's what your decimal should have looked like, something like that. Are we okay? If we did not get that, let me know, because we want to make sure we can hit the right buttons.
I'm looking over to the next slide.
Don't look yet. All right, what about 2 to the negative x? And I want you to tell me when x equals pi. So what is 2 to the negative pi power? Where's your calculator? Grab a calculator. Is it a positive or negative decimal? It's about 0.1133147-ish. All right. And then the last one, 0.6 to the x power when x equals 3 halves. Try that one. Yep. So, will I be asking you to do all math in your head in this chapter? Definitely not. Our calculator is our best friend in this chapter. There are some things, like tomorrow, some things I'll expect you to be able to do without a calculator. Okay? All right.
This is the one I was laughing at.
You're laughing at radioactive decay?
No, I'm laughing at the contrast, because you have this, like, happy thought, like
And that's radioactive decay?
Yeah.
You know, she's happy about the math. All right, so guys, in 1986, a nuclear reactor accident occurred in Chernobyl, what was then the Soviet Union. The explosion spread highly toxic radioactive chemicals, such as plutonium, over hundreds of square miles, and the government evacuated the city and the surrounding area. To see why the city is now uninhabited, how many years ago was that? How many years ago was that? Try again. 33. Thank you for doing math. 33. All right. To see why it's now uninhabited, consider the model. So this is considered an exponential model because my unknown variable is in the exponent. Okay, so those are exponential models. That represents the amount of plutonium, P, that remains from an initial 10 pounds, which was kind of elapsed into the atmosphere after T years. So how much plutonium remains today? So what we need to look at, we're going to use that exponential. So 10 times half to the, how many years? It's been 33 years divided by 24,100. Wait, what? 9.99? But I just want you to take into consideration, look at that. It has been 33 years since that accident happened. It started out with 10 pounds. 33 years later, 9.99. So you think they're moving back in anytime soon? But exponential growth or exponential types of formulas are very useful in the real world, okay? That one, if you ask your science teachers, that's your half-life formula. So very, very useful. That's frightening that that's still 9.99 pounds. All right. No, it's not 10, though. There's not still a full 10
I
pounds.
mean, obviously not.
A real mathematician does not round up. We like every digit there is. That's why I like fractions, because they're exact. All right, so using this formula, we can look at this for both exponential growth or exponential decay. So, for example, that what we just looked at with plutonium, would that be growth or decay? Thank you, Neil. You're right. It's a problem if that plutonium is growing, right? That is decay, very slowly, but it is decay. If you put money in the bank, you hope it's growth, right? You hope so. No? It may be very small growth, just like our decay problem, that plutonium, right? His debt is growth, his savings is decay. All right, so you should be able to tell if it's growth or decay just by looking at what this number is right there. Whatever the number is that's being raised to the exponent, you can tell if it's growth or decay. So if that b value is greater than 1, it is growth. Okay? And if that b value is between 0 and 1, because it's always going to be positive, if it's between 0 and 1, then that is decay. Does that make sense? Like if we look back at the problem we just did, that number is between 0 and 1. This is decay. It's getting smaller very, very slowly, but it is. All right. So is this first one, 12 times 0.95 to the x power, is that growth or decay? That is decay. Yeah, because this number right here is between 0 and 1, so it's going to be decay. And then this problem is growth. Are we alive today, guys? Because that number is greater than 1. Bigger than 1, it's growth. Now, does telling whether it's growth or decay care at all about what this a value is up front? It does not. Right, that one was decay even though that number was clearly bigger than 1. And that was growth even though that one is not. So that number is irrelevant. It's whatever number the exponent is attached to. You can tell if it's growth or decay. So this was just the example I actually brought up. If your parents put $5,000 into a college savings account when you were born and it pays 5% interest per year, growth or decay? That's going to be growth. That money is going to build interest and get larger over time. How large will it get? Okay? And we can figure that out. We're going to talk about some formulas today dealing with exponential functions that we can actually figure out how much money you're going to have at any given time.
This is the last chapter because it works as a leading.
No. It's only this section of this chapter that is a really strong tie-in to that. So like some of the formulas we're going to talk about today, like Neil has actually done in the financial class. He's already seen some of them. All right. Yeah, this takes it to a whole nother level, though, compared to his class. All right, so this is still the same type of formula, right? Here's my A. This is acting as my B, and then you have your exponent that we don't know. okay? So it's still the same a times b to the x. It's still that same formula that we started off with, except the b part is now going to be 1, and then it's going to be plus or minus, depending if it's growth or decay, and then whatever rate it is growing or decaying at. So we can figure out this actual problem. So here it is. I kind of rewrote it into a more user-friendly approach at the formula. So a times, instead of just b, it's now 1. I wrote plus or minus r because it depends on if it is growth, I will use the plus. If it's decay, I'm going to use the minus. Right? T is the time in years. Other time period could happen, but typically it's just years. A is the initial amount that you started with. And r is the percent of increase or decrease expressed as a decimal. So if I told you the rate was 3.2%, you wouldn't put 3.2 in there for r. What would you put?
0.032.
Yes. This you would convert to 0.032. How do you know to do that?
Because you have to move the decimal over 2 spaces to the left.
Very nice. If you take the financial class, you do that every single day. But yeah, any percent they give you, you have to move that decimal point 2 spots. Or divide it by 100, it's doing the same thing. Okay? Percents are always, mathematically, that's what you're doing when you move 2 spots. So, all right. So you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest rate. How much will be in the account after 6 years? So we're going to use our formula. My initial amount, my A value, is $1,000. Will it be growth or decay? Growth, so I'm going to use a plus. 5%, how am I going to write that one?
0.05.
Very good, so 0.05. And then what's my T value? The exponent at the time was 6 years. So literally, you're going to grab your calculator and you're going to type that entire thing in just as you see it.
You actually do have to round here and have more than like.
You are right. It comes out with 0.095641. That's all your calculator shows you. We're talking money. So money is always taken to the nearest cent. So that means it needs to be 2 spots. But you have to look at the number afterwards. If it's 5 or higher, it's going to round up to the next cent. So instead of 9 cents, it will round to 10 cents. And I am a stickler on rounding. If you are off by a penny, it is wrong. Because especially in that financial class, of course, Neil just walked out of here. If you were off by a penny in one spot and we just did, like, for example, 10 lines of an amortization table, which you were doing all kinds of calculations on, everything's going to be wrong because 1 penny was off. So dealing with money and things, you want to make sure you have every cent accounted for. All right, questions here? Yeah. If this was a 4, then that would stay 9 cents. All right, are you okay then? Okay. So what do you guys think? You put $1,000 in, you literally just let it sit in an account, and then when you took it out later, you had an extra $340. That's kind of not bad, right? That's free money. I mean,
Well,
it's free money. What if I had put like 10,000 in? If I put $100,000 in? We could plug those different values in and figure out what it's going to be. But yeah, I mean, you can see kind of how money does grow. Now there's different types of accounts, and we'll talk about all that coming up.
I was going to say, isn't like 5% annual interest like really high?
Yes, it is. It's very high. No, that's very high. All right, on this one, notice I highlighted the year 2030. Please change that on your notes. I think yours said 2020, I think was on yours. I've used this example for many years, and it used to be off into the future. Now 2020 is next year. Now I'm just old, and I've caught up with the year on my problem. All right, so the Lorax population is decreasing exponentially at a rate of 13% per year. If the current Lorax population is 101, how many will be left in the year 2030? So, again, going back to my formula. So y equals, my initial amount was 101 of them. Is it going to be plus or the minus? Minus. 13% will be written as 0.13. Good. And then time. How many years is it from now until 2030? That is 11 years.
So,
Okay. All right, so 101, then 1 minus 0.13 to the 11th power. What are we going to do here? So we get y equals 21.82 blah, 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 blah. This is not money. We are talking about a Lorax. So think about it if it was a person. Would you tell me 21 or would you tell me 22?
21.
You would tell me 21.
This they said this in my environmental science class.
Mhm.
Like population numbers.
Yeah, what did they say?
Like at 0.8 of a rabbit,
Right.
down always.
Good. So keep in mind the difference there, guys. The last problem we rounded up because we're talking about money and cents, and those are going to round up to the nearest cent. When you're talking about people or living objects, we're going to round down to the nearest whole one. Okay? I don't want half a person or somebody who's like 80% dead, right? I don't want that. Or 20% dead. Yeah, we're not getting into all that. Science, did you have a question? You could. With the two little squiggly lines. Yeah, you could. And that's kind of what this is, right? I could throw that in front of here. It's approximately, yeah, 21 Lorax. That's probably an even better answer for that. All right. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. I have a lot of you tech people in here. That's insane, right? 92% increase in viruses and whatnot. Write an exponential growth model giving the number n of incidents t years after 1996, and then about how many incidents were there in 2003. If I'm asking for the model, I'm just asking for set up your formula and then solve it for me. That's all I'm asking for, okay? Because your final exam, it's worded like that on there too, so don't panic. I just want, give me your equation and then give me the answer. Okay, so I'm going to use my model. So y equals, how many am I starting with? The 2573. Is it plus or minus? Plus. And my rate, 0.92. And then t.
The exponent's gonna be 7, but
Mhm.
but I mean,
For the model, just give me the equation. That's all I want. I just want to know what you did.
I thought you had to put in n.
You don't have to. No, you're good. You can just go ahead and give me the equation. That way I can see what you typed in your calculator. And then you actually type it in. Tell me what you get. So 2573, 1 plus 0.92. Yeah. So 247,480. It's 0.7. So again, would you round up or would you round down? I would round down on this one. Money, you're going to round up if it needs to be. Things like this, you can just round it to the nearest whole. Okay, so tech people, since I have a lot of you in here, do you think it's as bad now as it was in 96? With new technology, is it still terrible and on the rise that bad, or is it better now because we can combat all of this?
Not bad. Because, like, there are probably a lot more viruses out there, but there are also probably more computers, like, detrimental.
Because we have safeguards against them?
Yeah. Whereas in, like, 1998, nothing.
Right, this is back where people were first getting computers in their homes, right? Like when people were like trying to boot up in DOS, stuff like that. Did you guys use DOS?
I think they
My first computer at our house like was this big, like huge, and the screen was like this big. But it was huge. And I remember like it always booted up in DOS. So for a while I like knew how to like type things in DOS to like get it to run a program. I have no idea now. But yeah. But anyway, I remember that. I'm just dated myself. I'm old. Okay. So switch gears just slightly. We're going to look at compound interest. So kind of back to all the money stuff. Okay. So this is another formula that's just slightly different than the other one. What's the only part that changed? I have an initial amount. I just called it my principal amount this time, right? I still have the 1. If we're talking money, it's always going to be plus, right? We're not going to depreciate our money in the bank. We hope not. And then this time it has my rate divided by something. Yes, number of times it's compounded per year, and then that same number gets multiplied by how many years this time. So, but do you see how it's still the same type of formula? I still have the a times b to the x power. I still have that general form. This time I just kind of switched it. A few more things got added to it. Haman, would you like to give that to me now or later? Okay, put it away. All right, so P is my initial principal amount, the amount I'm starting with. R is still my rate expressed as a decimal. N is compounded n times per year. So let's kind of talk about that for a minute. If I told you it was compounded quarterly, how many times is that? That would be 4 times. What if I told you monthly? That is 12 times per year. What if I said semi-annually? It does. Where's my girls in here? Victoria's Secret semi-annual sales. How many times a year? What? It's twice. There you go, Hamid. Semi-annual means it happens twice a year. So quarterly, monthly, semi-annually. What if I said daily?
Wow.
360. We'll also assume it's not a leap year. 365. Okay. What if it's weekly? Because I can throw all of these at you. Weekly is 52 times. What if I said... What if I said it was bi-monthly?
No, 24.
It'd be 24.
Can you also mean once every 2 months?
Bi-monthly means twice a month. So there's 12 months times 2, so it'd be 24.
What is it?
What if it's semi-monthly?
Oh. That's going to be 6 then.
Not 6.
Wait, 24?
Nope. Oh, wait. Hold on. Hold on. It would be... I wrote that wrong. That's why you're confused. I wrote that wrong. I am so sorry. Scratch all that. Sorry. Bi-weekly and then semi-monthly is what I was going for. Sorry. That's why you're looking at me like I'm crazy. So bi-weekly. Twice. Or it's every 2 weeks is bi-weekly. Every 2 weeks would be how many times a year? 26. If there's 52 weeks and it's every other week, it's 26 times a year. But then semi-monthly would be twice a month. That's the one that's 24. If you didn't jot that list down, you may want to. And again, could I ask you hourly? Yep, I could. You'd have to figure out how many hours are in a year. Every second? You could figure it out, right? You could. It wouldn't be that hard to figure out. All right, and then A is the actual amount that you have in your account after T number of years. Okay? So depending how often your money is compounded depends on how fast it builds. So what's happening, just so you guys can kind of understand the difference. When you put money in your bank, and they're going to let you earn interest on it. Now granted, we're going to look at some interest rates that are a little higher than what you actually normally see a lot of times in a bank. But if it's just simple interest, which is what I think most people are familiar with, I equals PRT. You guys heard that formula before? That's simple interest, which is taking however much money you originally put in and you are earning interest only on your initial amount. So if I put $1,000 in and I let it sit in there for 30 years, every year it is only earning interest on the initial $1,000 I ever put in there. So every year we'll earn the same amount of interest, which is good, but not great, right? Because it's building. So compounding is taking my initial 1,000, and if I said it was compounded monthly, then it will earn interest for a month, and then it will take that interest at the end of the month and add it on, and now it's earning interest on the new amount for the next month. And then at the end of the month, it's going to take the interest I earned, it's going to add it on, now it's going to earn interest on that amount. So the amount it's earning interest on grows every single time. Does that make sense? As opposed to $1,000 for 30 years. That's all I'm ever earning interest on. That's a terrible system. So quarterly, monthly, semi-annual, all of this stuff, this is how often it is compounded. How many times in that year will they take the interest you just earned, add it on to the original amount, and then start earning interest on the new amount? That's what it's doing. Does that make sense? So how often does that number get bigger that it's earning the interest on? So obviously, the more it does it, the better, right? The faster it's going to grow, okay? Because like if I did it daily, every single day it's going to take that interest and add it on, add it on, add it on, add it on. So it's constantly every day earning interest on a higher value. Whereas if it's just yearly, then it's just once a year, right? So it takes the entire year before it takes the interest, adds on, and then it starts working off of that new amount. So we're going to kind of look at some comparisons here. So if $12,000 is invested in an annual interest rate of 9%, which is an unheard of, really high interest rate, find the balance after 5 years if it is compounded quarterly. All right, so I have your formula down in the corner so we can see it. So A equals, P is the principal amount, or the amount I started with, which in this case is $12,000. 1 plus my rate. How would you write 9%? 0.09. If you write 0.9, that is 90% interest, which will never happen in your lifetime, so don't write that, okay? All right, and then N, how many times is quarterly? That is 4 times a year. And then my exponent is 4 times, how many years? It asks for 5 years. Now, let's kind of talk calculators here. If you are using the graphing calculator, which I know most of you use when you're in here, typing this in is not a big deal. You should be able to type it in just fine. If you are using the scientific ones, scientific calculators do not like decimals typically within a fraction, so it's probably going to have a problem with that. And when you go to type in that exponent on a scientific calculator, you're going to have problems with that as well. So if you are somebody who's going to use a scientific calculator, you will literally have to have a division sign where that fraction is, because it doesn't like decimals in a fraction, and you would need an extra set of parentheses only if you're using scientific calculator. If you're using the graphing ones, they are very smart. They can do all of that without a problem. Okay? Common. Or you could just make it 20. Yes, absolutely. That'll save you from an extra set of parentheses. All right, so after 5 years, if it was compounded quarterly, we should have $18,726.11 in that account. I have 11 cents. Take it we did not get 11 cents? 0.11041? I heard many people like groan at me. No? If you did not get 11 cents, double check what you typed in. You okay? All right. How much would this same investment yield if it were compounded monthly? Before we even figure it out, should it make more money or less money? More. The more often it's compounded, the more I should make. All right, so I need to change some numbers in my formula then. 1 plus my rate's still 9%, but now monthly is how many times a year? 12. And that changes my exponent to 12 times 5.
Don't bother rewriting. Like, arrow up.
Yes, you can. Yep, you can arrow up. When we use these formulas, trust me, ask my financial kids, they arrow into their formulas like crazy. Just arrow up so it's highlighted in black and hit enter. And it'll bring it back up so you can actually arrow into it then.
Like that lower amount is definitely not right.
You're right. It should not be lower. You should get $18,788.17.
Yeah, I got
You did not change the 4
Oh.
right there to a 12.
Yeah.
All right, anyone not able to get all of that to work? You were supposed to change the 4, not the 5. Ben, did you have a question? Oh, because of how your rate is divided out, because you didn't divide this and you're not compounding. The exponent, as you make that bigger, that's the more times it's being multiplied by itself. And you kept a smaller number by not multiplying the n times the t. So it's not compounding itself as often. Right, so when you do it without that, Ben, it's as if it was just once a year. That's what it's looking at. It's a lot of formulas, yeah. All right, so you deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded with the given frequency. So just using our formula, let's make sure we can do this. Okay? So y equals, or a equals, sorry, my principal amount, which is 4,000, 1 plus my rate. How would you write 2.92%?
0.0292.
Good. Remember, you're moving that decimal point 2 spots when you're doing that. And if it's quarterly, how many times is that? That is 4. And it's 4 times, and it's just asked for 1 year. That's fine. 4 times 1, 1 times 4, doesn't matter. All right, so quarterly, we should get $4,118. How many cents? That would be 9 cents. Be careful, it's got an 8, and then there's a 5 after it, which is going to make that round up to 9 cents. Okay, same amount, but what if I went daily? Should it be more or less? Should be more, because I'm compounding it more often. Daily is going to be $365. $4,118.52. Now, that last one, there was a bit more difference. Why is this one only change difference? Quinn? It's only 1 year. And what else is way different from the last one? Dylan? Not necessarily. Daily is good because that means it's compound. It's adding on every time. It's a lower interest rate. It's a much lower interest rate. So before I was looking at like 5 years. Now I'm looking at 1 year. Before I had a 9%. This time I have a 2.92%. Right. So less interest rate. It's less amount of time. So you're going to see a smaller change.
2.92 is still pretty high.
Yes. Yes. That's a really good interest rate. Yeah. This should be 0.0292. Yeah, I can move the decimal 2 spots. All right, guys. So let's kind of see what happened here. So when you plugged in a 1, you should have gotten 2. That's what you should have gotten. If I plug in a 10, 2.594. You plugged in 100, 2.705, 1,000, 2.717, 10,000, 2.718, 100,000, 2.718. Didn't change. Yes.
I was doing 2.
I said 3 like 6 times.
I did.
Yeah. Yeah, I told you. But anyway, as far as looking at all of this, I'm trying to get you to see what's going on. Like, do you see, obviously it's getting closer and closer and closer, and then it's kind of like stalemating at like 2.718. That's an actual number in math. It's E. Can you guys look at your calculators? Can you find an E? Not a capital one, a lowercase e on your calculator. No, that is switching it to scientific notation. All right, so does anyone not see the E? If you look on your graphing calculator, it is above the button that says ln. Like you found log, below there is ln, and above that in blue it says e to the x power. We will be talking in the days coming up about both the log button and the button that says ln. That actually stands for natural log, but it's ln, not nl. That's natural log. I didn't make the rules. But e is like the opposite of a natural log. Kind of like when we had cubed roots, you would cube it. They kind of undid each other. E and natural log undo each other. Okay? But e is an irrational number, just like we have pi. If I asked you guys what pi is, you could probably tell me the first digits, right? Right? Everybody knows 3.14. You can at least give me that far, right? 3.1415926. That's as far as I know. Sure. Anyway, but pi is one of those numbers that we use a symbol for. Do you know what pi actually is? Not that pi. I heard circumference. It is circumference divided by the diameter. You were close. So in other words, if you would take your, I used to do this experiment with my kids years ago. If you would take the circumference of your head and divide it by the diameter of your head, how far it is from one side to the other, you'd get pi. 3.14. You would. But anyway, so like pi is a number. We use a symbol to represent it. Same thing here. E is a number, but we use the letter E to represent that, just like we do with pi. All right. So e to the x power. So e is a number that no matter what, when you use it, you have to tell it what exponent you want. So if you look at your calculator, that's why it says e to the x on here. So go ahead and type that in. So you would have to hit the blue button, the second, and then ln. And it comes up with e, and it automatically pops open the exponent. So if I would put a 1 in there, e to the first is just e, right? Hit enter. You got to hit second first.
I know.
ln's right there. So if I do e to the first, we got that 2.718, blah, blah, blah. The same number that we were just looking at. So that's where it comes from, though. E comes from where 1 plus 1 over x to the x power, as it approaches, this stands for positive infinity, meaning as the number of x, as this number gets bigger and bigger and bigger and bigger, it stops. It kind of stalemates here. You're never going to move beyond this. I know, who sits around and thinks up this stuff, right? So let's just get some calculator button push and practice at this point. It's kind of what we're looking at. If I have e to the x power, what if x is negative 2? So in other words, I'm asking what is e to the negative 2 power equals what? Okay, so 0.1353. I'll just give me 4 decimal spots. Okay, if I do e to the negative 1. 0.367. If I round to 4 decimals, that would technically round that to a 9. Okay, see the decimal after that, or the digit? Okay, about e to the 0.25. 1.2840. And then e to the negative 0.3. So just to 4 digits, so 7408. So e, yes, it's a letter, but it actually is a number, the same way the pi symbol actually stands for a number, okay? All right. So we use e. There is many formulas that use it, but one in particular is if it is continuously compounded interest. So we did compounded interest. I could do daily, monthly, weekly. Well, I can do all those options, right? What about if it's continuously compounded? Every second of every day, whatever interest I'm earning, it just keeps adding back on constantly. Never stops.
That'd still be secondly, though.
Is what?
Like, you could hypothetically break down every unit of time into a smaller unit of time,
That's why we use e.
but continuously isn't.
A is the amount after t years. I know where you're going with that, but that's a whole separate side conversation. P is our principal again. R is still the interest rate as a decimal. So same variables are just arranged differently for our formula. This one I always just call it the APERT formula because it's PERT, P-E-R-T. PERT. That's how I always reference it. All right, so you deposit $2,500 in an account that pays 5% annual interest compounded continuously. So the biggest thing students always are like, well, how do I know which formula to use? That's like always a common question. You're like, we've looked at quite a few different ones. How do I know which one? If it says it's compounded continuously, you use the one with E in it. Okay, if it just says compounded whatever, use the last one we just looked at. And if it doesn't use the word compounded anywhere in it at all, you use the first formula we talked about. Yes, we will. Oh, you want it on colored paper? Okay. All right, so what if I do this for 2 years? So A equals the principal amount, which is 2,500, times E to the RT. So my 5% is written how? 0.05 times my T. This one asks for 2 years. Again, make sure we know how to type all this stuff in, guys. This is definitely a section where if you can't use a calculator, you're going to struggle. So 2,500, and then E to the 0.05 times 2. Again, if you are using a scientific calculator, because this button is on there, you will need extra parentheses around your exponents. Good, so 2762.93 is correct. Make sure you're rounding to the nearest cent. I will count you wrong if you write 92. All right, so what if I did it for 5 years? 2,500 E 0.05 times 5. Again, if you're calculator savvy, just go back up and change one number in it. Dylan, are you calculator savvy? So 3210 and 6 cents. $3,210.06. And if I went 7.5 years, 2,500 E to the 7.5 times 5. Oh, did I change that to 7.5? What was I changing? That was wrong. 0.05 times 7.5. Sorry. So 36, 37, 48. So I told you I'm going to count off if you round incorrectly. What else would force me to take a point off? Something basic that you should always have. $sign. Please make note so I don't get really angry at you later. Where does the $sign go? It's first, right? Nothing is more frustrating than somebody who sticks the $sign at the end. I literally see people, like, instead of writing like $100, they write this. You look stupid when you do this. I'm going to tell you that right now. Don't do this. You look dumb. So, just so you know, don't, I may take off max points of your entire test if you do this, because this just drives me nuts.
0 points.
Right? Yeah, 0 points in the exam because you did that one time. Because just don't be that ignorant person, okay? You just look dumb. That is a $100 mistake. Don't do that. All right. So these were your three formulas, right? You had your exponential growth and decay. So I know to use this one because it will not say compounded anywhere in the problem. Okay? So that's how I know to use this one. And I did break down for you so you know what everything stands for. Your compound interest and continuously compounded, it will literally say the word compound in the problem. I know to use this one. And that one I know to use because it'll say compounded, but it will also say continuously compounded. And how do I know to use this one? It doesn't say compounded. Yeah, makes sense. It's going to be talking about some kind of growth or decay. It's increasing or decreasing or something for that. All right. So we do have worksheet 7172. I want to make sure you have time. Yeah, we got some good time in here. So you can get it done. Ask me if you need help, things like that. Questions before I pass it out? Awesome.